Hello, I am Dr. Sutishrubha Bhorali and I welcome you to this lecture video on Foundations of Artificial Intelligence, which is a part of the online course on Generative AI for Everyday Life. But before we understand what Generative AI is, we must know what artificial intelligence is. In this lecture video, we will discuss about artificial intelligence, the evolution of artificial intelligence over the decades, and the foundational core concepts of artificial intelligence, including knowledge representation, machine learning, and natural language processing. Let's begin with the definition of artificial intelligence. There is no fixed one definition of AI. So let us see a few definitions of artificial intelligence. The first definition is from John McCarthy, who is considered as the father of artificial intelligence. According to him, artificial intelligence is the science and engineering of making machines intelligent. The second definition is from the European Commission's high-level expert group on AI. In their document, they have defined artificial intelligence as artificial intelligence refers to systems that display intelligent behavior by analyzing their environment and taking actions with some degree of autonomy to achieve specific goals. Now let us see how Oxford English Dictionary defines artificial intelligence. Here, AI is defined as the capacity of computers or other machines to exhibit or simulate intelligent behavior. The next definition of AI is taken from Niti Aayog, National Strategy for Artificial Intelligence, where AI is defined as a constellation of technologies that enable machines to act with higher levels of intelligence and emulate human capabilities to sense, comprehend, and act. Now that we have seen the various definitions of AI, let us deep dive into the history of artificial intelligence. The history of artificial intelligence began in 1950s when Alan Turing, a British mathematician and pioneer in computing, laid the foundation for artificial intelligence with his groundbreaking paper Computing Machinery and Intelligence, and asked the question, can machines think? Turing proposed the Turing test in his paper, which is a method to evaluate a machine's ability to exhibit intelligent behavior, indistinguishable from a human. In this test, if a human interrogator cannot reliably distinguish between the responses of a human and a machine during a conversion, the machine is considered to have thought. This idea marked a critical step in conceptualizing AI, sparking debates about machine intelligence and influencing the development of early AI systems. The period from 1956 to 1974, often called the golden years of AI, marked significant progress in artificial intelligence, particularly in knowledge-based systems. Researchers developed foundational systems like logic theorists and general problem solver that mimicked human reasoning. Knowledge-based systems such as Dendrel for chemical analysis and Mycin for medical diagnosis emerged, leveraging domain-specific knowledge to solve problems. This era saw optimism about AI's potential, driven by advancements in symbolic reasoning and problem-solving techniques, laying the groundwork for future AI innovations. Let's look at some of the important events in this time frame. The term artificial intelligence was coined in 1956 during the Dartmouth Conference, which brought together pioneers in the field like Dr. Marvin Minsky, Dr. John McCarthy, Professor Herbert Simon, Dr. Claude Shannon, and Mr. Nathaniel Rochester, among many. In 1959, Arthur Samuel developed the first learning program for playing checkers, pioneering machine learning. This program refined its strategy by analyzing game outcomes, eventually defeating human-designed programs, a groundbreaking achievement demonstrating computers' potential for self-improvement. In 1961, IBM introduced Shoebox, a voice-controlled arithmetic device capable of recognizing spoken digits and basic mathematical operations. Shoebox marked a milestone in speech recognition, showing early potential for voice-commanded systems. In 1966, Shaky was the first mobile robot to use artificial intelligence to navigate and reason about its surroundings. Developed at Stanford Research Institute, Shaky combined computer vision, movement planning, and logical reasoning to navigate its environment autonomously. This innovation laid the foundation for modern autonomous robotics. The same year saw the development of ELIZA by Joseph Weizenbaum at MIT, an early example of natural language processing or NLP. ELIZA simulated a conversational therapist using a pattern matching technique, engaging users in simple dialogue. While limited in understanding, ELIZA demonstrated the potential for human-computer interaction, inspiring future conversational agents. From 1974 to 1980, the field of artificial intelligence experienced its first significant downturn, known as the AI winter. Early optimism gave way to disillusionment as ambitious promises of AI pioneers failed to materialize due to technical limitations. Funding and interest waned as AI systems struggled with computational inefficiency, lack of data, and scalability issues. From 1980 to 1987, artificial intelligence experienced a significant resurgence, marked by the boom of the expert systems. Expert systems gained widespread adoption in industries such as healthcare, finance, and manufacturing. This era's advancements were driven by increased funding and improved computational power, demonstrating AI's practical utility and establishing it as a valuable tool in industrial applications. From 1987 to 1994, the field of artificial intelligence faced its second major downturn, known as the second AI winter. This decline was triggered by high expectations, failing to match practical outputs, leading to reduced funding and interest. The collapse of the Lisp machine market, which had been central to AI research, further worsened the situation. Expert systems proved expensive and difficult to maintain, causing industries to lose faith in their utility. Despite these challenges, foundational work during this period quietly set the stage for AI's revival in the late 1990s. The period from 1997 onwards has been pivotal for AI, marked by groundbreaking advancement that demonstrated its growing potential. Let's look at some of the important events in this time frame. In 1997, IBM's Deep Blue made history by defeating world chess champion Garry Kasparov, showcasing AI's ability to master complex strategic games. In 1999, NASA's Remote Agent autonomously piloted the Deep Space One spacecraft, demonstrating AI's application in space and exploration. In 2000, Kismet, a robot capable of expressing emotions, highlighted AI's role in human-robot interaction. By 2004, Honda released Asimo, a personal robot with advanced mobility. That same year, NASA developed AI-based planners for rover operations, streamlining space missions. In 2005, the DARPA Grand Challenge saw autonomous cars complete a challenging desert course, paving the way for self-driving vehicles. By 2009, NASA deployed AI systems for robot control and motion planning. In 2011, IBM's Watson defeated Jeopardy champion Ken Jennings, showcasing AI's language processing and reasoning capabilities. The introduction of generative adversarial networks in 2014 revolutionized AI's ability to create realistic synthetic data. In 2016, AI achieved new milestones with AlphaGo, defeating human champions in the complex game of Go. In February 2016, Sophia became the first non-human to be recognized with legal personhood, showcasing advancements in humanoid robotics and AI integration. Developed by Google, DeepMind introduced WaveNet, a neural network capable of generating human-like speech, marking a breakthrough in natural language processing. OpenAI introduced GPT-3 in 2020, a language model capable of performing diverse tasks without specific training, marking a significant advancement in AI's language understanding. These milestones reflect AI's transformative impact across domains, from gaming and robotics to autonomous systems, natural language processing, and content generation. Let us now look at the different categories of AI. On the basis of capabilities, AI can be categorized into narrow AI, general AI, and super AI. Narrow AI, also known as weak AI. These artificial intelligence systems are trained to perform a single or narrow task, often far faster and better than a human mind can. Examples of narrow AI are digital assistants like Amazon's Alexa. General AI or strong AI systems would have the ability to perform any intellectual task a human can do and potentially do so with greater efficiency. These AI systems are a theoretical concept today, as current AI systems have not reached this level. Super AI is a form of AI that surpasses human intelligence across all fields, including creativity, problem solving, and social skills. These AI systems could outperform humans in every domain, potentially leading to profound societal transformations. Though for now, like general AI, super AI is also theoretical. On the basis of functionalities, AI can be divided into 4 categories: reactive machine AI, limited memory AI, theory of mind AI, and self-aware AI. Reactive machine AI is the most basic form of AI that operates solely based on the current input without memory or past experience. These systems cannot learn or adapt. They only react to specific situations programmed into them. IBM's Deep Blue, the chess-playing computer, is a reactive AI. It analyzes the current state of the chessboard and calculates the best possible move, but lacks the ability to learn or strategize beyond its programming. Limited memory AI builds upon reactive machines by incorporating the ability to learn from past data to some extent. These systems can use historical data to inform decisions, but their memory is temporary and task specific. For example, self-driving cars utilize limited memory AI. They analyze traffic patterns, recognize road signs, and predict the movement of nearby vehicles based on previously collected data, enabling them to make real-time decisions. Other examples include generative AI tools like ChatGPT and virtual assistants like Siri and Alexa. Theory of mind AI aims to understand emotions, beliefs, and thought process in humans and other entities. It seeks to simulate human-like social intelligence to enhance interaction and decision making. For example, a virtual assistant with theory of mind AI would not only understand commands but also interpret the user's mood or user's intent to respond more empathically. For example, it could sense the frustration in a user's tone and adjust its responses accordingly. Self-aware AI is the most advanced and hypothetical form of AI. These systems would possess self-consciousness, awareness of their own existence, and the ability to understand and express emotions. They would function similarly to humans with complete autonomy and intelligence. For example, a self-aware robot could recognize its own needs and motivations. For instance, it might understand that its battery is running low and autonomously decide to recharge, while also considering the impact on ongoing tasks. Let's take a moment to assess your understanding with a couple of quick multiple choice questions. This will help you review and reinforce what we have covered in this tutorial. Here is the first question. What was the significance of Alan Turing's paper, Computing Machinery and Intelligence? Take a moment to think about your answer. The correct answer is option B. It proposed the Turing test to evaluate machine intelligence. If you got it right, well done. If not, don't worry. You can revisit the explanation in the video. Here is the second question. Which type of AI builds upon reactive machines by incorporating historical data for decision making? Take a moment to think about your answer. The correct answer is option B, limited memory AI. Now, let's move on to the next section. Let us now look at the core concepts of artificial intelligence. The core concepts of artificial intelligence form the foundation for creating intelligent systems. The foundational core concepts of AI, including knowledge representation, search and optimization, machine learning, natural language processing, artificial neural networks, robotics and control systems will be discussed in this video lecture. The first concept is search and optimization. Search and optimization are fundamental concepts in artificial intelligence, enabling systems to explore vast spaces of possible solutions to find the best or most suitable answer to a given problem. These techniques are essential for solving complex tasks where direct solutions are not readily apparent. AI leverages search algorithms to navigate and evaluate possible states, systematically determining the optimal or near optimal path to a goal. Optimization focuses on refining these processes, often balancing constraints and efficiency to achieve desirable outcomes. Different techniques be it uniform search techniques like breadth first search and depth first search, or informed search techniques like ASR algorithm are used. Some of the applications are finding the shortest route in navigation systems or robotics, developing optimal moves in games like chess, and allocating resources or tasks efficiently, such as airline timetables or manufacturing processes. The next core concept is about knowledge representation. Knowledge representation is a fundamental concept in artificial intelligence that deals with how information about the world is structured, stored, and used by machines. Its primary goal is to enable a system to understand and manipulate data in a way that mimics human reasoning. A well-designed knowledge representation system allows artificial intelligence to solve complex problems, draw logical inferences, and make decisions. Different techniques are used to model knowledge, such as logic-based representations, semantic networks, ontologies, and frames. Some of the applications of knowledge representation systems are in the form of expert systems. MyScene is a medical diagnostic system that provides specialized advice based on a knowledge base and reasoning, assisting doctors in diagnosing diseases. Another example are recommendation systems designed for platforms like Netflix or Amazon to suggest movies or products based on user preferences and behavioral data using collaborative or content-based filtering. The next core concept of AI is machine learning. Machine learning is a subset of artificial intelligence that enables systems to learn patterns from data and make predictions or decisions without being explicitly programmed. Core ideas of machine learning are supervised learning, unsupervised learning, and reinforcement learning. In supervised learning, models are trained using labeled data, where each input is paired with a corresponding output. The system learns to map inputs to outputs and generalize this mapping for new unseen data. For example, predicting house prices based on features like size, location, and number of rooms. Unsupervised learning deals with unlabeled data, where the goal is to uncover hidden patterns or structures in the dataset. Common techniques include clustering and dimensionality reduction. For example, grouping customers with similar purchasing behaviors for targeted marketing. Reinforcement learning involves learning through interaction with an environment. The system receives rewards or penalties based on its actions and aims to maximize cumulative rewards over time. For example, training a robot to navigate a maze by rewarding it for reaching the exit. Some of the applications of machine learning are in the field of image recognition, where machine learning powers systems to identify objects, faces, and handwriting in photos and videos. Its application can also be seen in fraud detection, where algorithms analyze transaction patterns to detect anomalies that might indicate fraud. The next core concept of artificial intelligence is natural language processing. Natural language processing is a branch of AI that focuses on enabling machines to understand, interpret, and respond to human languages. By bridging the gap between human communication and computer understanding, NLP allows machines to process, and analyze large amounts of natural data effectively. The core tasks in NLP are syntax analysis, semantic analysis, and language generation and translation. In syntax analysis involves analyzing the grammatical structure of sentences to identify relationships between words. Parsing helps machines understand sentence construction, such as subject-verb-object relationships. For example, the sentence, "The teacher explained the concept clearly," has the subject, the teacher, verb, explained, object, the concept, adverb, clearly. Semantic analysis focuses on understanding the meaning behind words and phrases. This involves resolving ambiguities and deriving context-based meaning. For example, determining whether the word bank refers to a financial institution or a river bank based on the sentence. Language generation and translation involves generating coherent, contextually relevant text or translating one language into another. It helps machines produce human-like responses or content. For example, AI translating English text to Assamese or generating a summary of a document. Some applications of NLP are chatbots, where NLP powers virtual assistants like Siri or Alexa, enabling them to process voice or text commands and provide meaningful responses. In sentiment analysis, analyzing text to determine emotional tone, such as identifying customer sentiment in reviews as positive, negative, or neutral. In machine translation, using tools like Google Translate, where NLP is used to convert text between languages while preserving the context and meaning. ChatGPT is a prime example of natural language processing in action. It uses advanced NLP techniques to understand, interpret, and generate human-like responses in text form. Another core concept of AI is artificial neural networks. Artificial neural networks are computational models inspired by the structure and functionality of the human brain. They are designed to process and analyze data by mimicking how biological neurons transmit and process information. Some of the key concepts in ANN are layers, activation functions, and backpropagation and training. Layers can be input layers which received raw data inputs to the network, or hidden layers which process inputs using interconnected nodes that apply weights and biases to extract meaningful patterns, or output layers that produces the final output such as prediction or classification. Activation functions introduce non-linearity to the network, enabling it to model complex relationships in data. Common activation functions include sigmoid. Backpropagation is a learning algorithm used to adjust weights and biases by minimizing the error between predicted and actual outputs. The process involves propagating errors backward through the network and updating weights using techniques like gradient descent. Some applications of artificial neural networks are in deep learning, speech recognition, and image classification. ANNs serve as the foundation for deep learning, enabling advancements in fields like natural language processing and autonomous systems. ANNs power systems like virtual assistants, enabling accurate interpretation of spoken language. In image classification, technologies like facial recognition and object detection rely on ANNs for analyzing and categorizing images. Another core concept of artificial intelligence is robotics and control systems. Robotics and control systems focus on developing intelligent systems that can perceive, interact with, and manipulate the physical world. These systems integrate hardware and software to perform tasks autonomously or semi-autonomously, combining sensing, decision-making, and actuation. The core ideas include sensing, actuation, and decision-making. In sensing, robotic systems gather data about their environment using sensors like cameras, LIDAR, ultrasonic sensors, or gyroscopes. This sensory input helps the robot understand its surroundings, detect obstacles, and monitor internal states for navigation, positioning, and task execution. Actuation enables robots to perform physical actions such as moving arms, wheels, or legs. These actions translate decisions into movements, enabling the robot to interact with its environment, be it gripping objects, assembling parts, or navigating terrain. In decision making, robots use algorithms to analyze sensory input and plan their movements. Decision making involves path planning, task prioritization, and adapting to dynamic environments. Techniques like machine learning and reinforcement learning often enhance this capability. Some applications are industrial robots, where these robots perform repetitive high-precision tasks like assembly, welding, or packaging in factories, significantly improving the productivity and quality. In autonomous vehicles like self-driving cars use sensors, AI, and control systems to navigate roads, avoid obstacles, and ensure passenger safety. Unmanned aerial vehicles utilize robotics and control systems for tasks like aerial photography, surveillance, and agricultural monitoring. Now that we have covered the key concepts in this part of the tutorial, let us take a moment to assess your understanding with a couple of quick multiple choice questions. This will help you review and reinforce what we have covered in this tutorial. Here is the first question. Which of the following is an application of robotics and control systems? Take a moment to think about your answer. The correct answer is option C, performing repetitive tasks like welding in factories. If you got it right, well done. If not, don't worry. You can revisit the explanation in the video. Here is the second question. Which AI concept mimics the structure of the human brain? Take a moment to think about your answer. The correct answer is option B, artificial neural networks. This brings us to the end of this video lecture. In this video lecture, we have discussed the definition of the term artificial intelligence from multiple sources. We have also delved into the fascinating history of artificial intelligence from 1950s to the present day. The different categories that AI systems could fall into have also been discussed in this video. The foundational core concepts of AI, including knowledge representation, search and optimization, machine learning, natural language processing, artificial neural networks, robotics and control systems have also been discussed in this video lecture. So thank you for watching this video.